In this second video on sequential logic, I will discuss the analysis and design tools for sequential circuits and present some design examples. As the analysis tools, we are going to discuss 5 items. These are the circuit diagram, the state table, also known as the state transition table, the state diagram, the state and output equations. We will also introduce input-output equations, or to be more exact, we can say flip-flop input equations and circuit output equations. Here is an example circuit diagram. Of course, we are already familiar with logic circuit diagrams from the videos on Boolean algebra and combinational logic. What's different here is only that we have memory elements, namely flip-flops, as well in our circuit diagram. In this example, we see 2 SR flip-flops whose outputs are called as A and B. The rest of the circuit consists of logic gates. The circuit has one input X and one output Y. Also, the clock signal connected to the flip-flops indicates that the circuit is a synchronous logic circuit. Using the circuit depicted here, we can evaluate the R and S inputs of the A and B flip-flops for any given state of these flip-flops and the input X. In that way, we can evaluate the next states, that is, the logic values A and B signals will carry whenever the next clock pulse arrives, as well as the output Y. Tabulating next states and the outputs with respect to the present states and input, we can write down a state table, also called state transition table. For example, if input X is given as 1 and the present state of the circuit is specified as A equals 0 and B equals 0, by following the interconnections in the circuit, we can see that the S input of flip-flop A turns out to be 0, whereas the R input is 1. That means the A flip-flop will be reset, that is, keep its 0 state in the next clock cycle. On the other hand, for X equals 1 and A equals 0, the S input of the B flip-flop will be 1 and its R input will be 0, causing its state to go to logic 1 level during the next clock pulse. Therefore, if the states A, B are 0, 0 and X equals 1, the next state will be 0, 1, as we read from the third column of the first line of this table. You can check the whole table in the same way by yourselves. The state table can also be put in a format to which we are more familiar from the combinational circuits. In this form, the present states of the flip-flops and the inputs are tabulated so as to resemble the inputs in a truth table, whereas the corresponding next states, together with the output of the circuit, are shown as the output columns of this truth table. This arrangement of the state table may be more useful for the design purposes, as we will see in a while. We can represent the state transitions and outputs shown in this table in a pictorial way as a state diagram. We have 2 flip-flops in the circuit, and therefore the state of the circuit can be expressed in 2 bits. The first one being the value of A, and the second one the value of B. So we have 4 states which the flip-flop outputs can exhibit: 0, 0, 0, 1, 1, 0, and 1, 1. The first line of the state table tells us that if the circuit is in state 0, 0, and if the input X is 0, then the next state will again be 0, 0, and the output will be 0. This information is shown on the state diagram by an arrow outgoing from 0, 0 and pointing to the same state. The input and output values are indicated on this arrow as separated by a slash. The input is written to the left of the slash sign and the output is on the right. In the first line of the state transition table, We also read that for x equals 1, the transition from 0, 0 is to state 0, 1. This can be shown on the state table by an arrow from 0, 0 to 0, 1, which is denoted as 1/0. Similarly, if the circuit is in state 0, 1 and the input is 0, the transition in the next clock pulse is to state 1, 1 and the output is 0. On the other hand, if x equals 1, this state will be kept as the next state and the output y will be 0. Proceeding in this way, we can carry the state transitions given in the state table to our state diagram. Note that the output is 1 only if the state transition is from 1, 0 to 0, 0 and x is equal to 1. Otherwise, the output is 0. So in the labels of all arrows other than this one, a 0 appears after the slash. Also, since the input x can be either 0 or 1, there are two arrows that come up from each state. One labeled with a 0 before the slash and the other with 1. Of course, if we had two inputs in the circuit, there would be 4 arrows emerging from each state. In general, the number of transitions starting from each state for a circuit with n inputs is 2 to the power n. To represent these state transitions in algebraic expressions, we can regard the state transition table as a truth table that describes the behavior of the next states and outputs as a function of the present states and the inputs. Here, for example, inspecting the table for combinations where the next state of the A flip-flop is given as 1, A of t plus 1 can be written as a sum of 4 minterms of A, B, and x, namely as A prime B x prime or A B prime x prime or A B x prime or A B x. You can also take x prime out of a parenthesis to have a somewhat simpler expression. Similarly, the next state of the B flip-flop can also be written as a sum of minterms from the state transition table. These two equations expressing the next states as a function of the present states and the input are known as the state equations of the circuit. State equations, together with the output equation, that is y equals a b prime x for this circuit, represent the behavior of a sequential logic circuit completely. In fact, we can use combinational logic tools for simplification of algebraic entities also to simplify such state equations. Writing down the Carnot map of a of t plus 1 as a function of x, a, and b, we can simplify it to a 3-term standard sum, or further to an expression as bx prime or a ended with b or x prime. The state equation for b can be simplified in the same way to a prime x or b ended with a prime or x. In fact, we could have obtained these equations also directly by using the characteristic equations of the flip-flops in the circuit. After all, the characteristic equations too represent the next state of flip-flops in terms of their present states. Flip-flop A is an SR flip-flop. Remember, the characteristic equation of SR flip-flop is A of t plus 1 equals S or R prime A. Inspecting the circuit diagram, we see that S input of the A flip-flop is obtained as Bx prime and the R input is B prime x. Substituting these expressions in the characteristic equation, we obtain the state equation which matches the one we simplified from the Carnot map. The characteristic equation of the B flip-flop is written as P of t plus 1 equals S or R prime B. Checking the circuit for the inputs of this flip-flop, we see that S is equal to A prime X and R is equal to AX prime, which yield the state equation for B. Also, the output equation is clearly seen from the circuit as Y equals A B prime X. One last possible way of describing the behavior of a sequential logic circuit is by specifying its flip-flop inputs and the output of the circuit. The inputs of the A flip-flop can be written as SA is equal to BX prime and RA is equal to B prime X. Similarly, for B flip-flop, we have SP equals A prime X and RB equals AX prime. Note that writing the flip-flop inputs in this way carries also the information about the number of flip-flops in the circuit and about the type of the flip-flops. Therefore, if we are also given the circuit output equation, we have all the information we need to redraw the circuit diagram or to derive the state equations. That completes 5 tools of analysis for sequential circuits, namely circuit diagram, state transition table, state diagram, state equations, and flip-flop input and circuit output equations. Let us now continue with the design tools. Some techniques which we have used in the design of combinational circuits, for example Carnot maps, are also useful in the design of sequential circuits. Nevertheless, there are also some other tools which we have to consider exclusively for sequential circuits. One of them is the state reduction. If the same objective can be accomplished by two alternative state diagrams, one would expect that the one with less number of states would be implemented with a simpler circuit. The main aim of state reduction is to reduce the number of flip-flops while keeping the input-output relationships of the circuit. However, since 2 to the power n different states can be implemented by n flip-flops, the reduction in the number of states may not always mean a reduction in the number of flip-flops. For example, a circuit with 12 states will require 4 flip-flops. Reducing the number of states to 10 would not change the number of flip-flops. You can reduce the number of flip-flops to 3 only if you can reduce the number of states to 8 or less. Also, in some cases, the reduction in the number of flip-flops can complicate the combinational part of the circuit. Due to all these reasons, the design of sequential circuits may turn out to be a trial and error process. In many practical cases, even if the transitions among the states of a circuit are defined according to the sequence of tasks to be executed by the circuit, the binary values of the states may still have to be determined by the designer. In that case, the relevant question is how to choose the binary values of the states to simplify the design procedure and its result, that is the circuit. Last but probably the most important design tool is the excitation table. Excitation tables show what the inputs to the flip-flops in the circuit should be so that the desired states can be reached from the present states. We will now discuss these 3 design tools a bit more and try to exemplify them. First, start with state reduction. Here is an example state diagram. By using state reduction, we would like to find a simpler diagram which can generate the same input-output relationship as in the state diagram. To clarify what we mean by input-output relationship, let us consider an input sequence that could be applied to this circuit. This sequence of inputs will cause a series of state transitions, and it will generate an output sequence, both of which can be followed by inspecting the state diagram. Reducing the states will almost certainly change the sequence of state transitions, but what we would like to keep is the output sequence. In fact, we would like to keep not only the output sequence corresponding to the input sequence given here, but the output sequences corresponding to all admissible input sequences. In other words, the state transitions defined by the new state diagram may be different. Nevertheless, any input sequence must yield the same output sequence generated by this state diagram. To reduce the number of states under such constraints, we will make use of the equivalent states. Two states are called equivalent if for each member of the set of inputs, they produce the same output and send the system to the same state or to an equivalent state. Equivalent states are more easily located on the state table rather than the state diagram. If we can find such equivalent states in our state table, then we can delete the row of the state table which contains such a state as the present state, and we can replace all its occurrences by the equivalent one. For example, for the present states called E and G in this table, the transition is to the same next state for x equals both 0 or 1. Also, these states result in the same outputs. Therefore, we can get rid of one of them, say G, and replace all G states with E. Once we do this, we recognize also the states D and F as equivalent states. So we don't need both of them. We can delete F and we can write D wherever we see the state F. These manipulations reduce the number of states to 5 without changing the input-output relationship of the circuit. The state diagram corresponding to this state transition table can be drawn as this. Having reduced the state diagram and table to a simpler one, we still do not have any binary values to represent 5 states in our table. Obviously, we need at least 3 flip-flops to implement these 5 states. Assuming that we are totally free to choose any 3-bit value for a state, we have 2 to the 3 options for the first state. Once having fixed the value of one of the states, we can assign a binary value to the second state other than that we used for the first one. Proceeding in this way, we can conclude that the number of possible state assignments are the product of integers from 8 down to 4. In other words, 6,720. Considerably large even for such a small number of states, isn't it? Nevertheless, there are some commonly used assignments which may be generally advantageous in the design process. For example, you can be as simple as possible in choosing the state values and go directly for the first 5 3-bit numbers. Another possibility is to use symbols of a 3-bit gray code, which may offer some conveniency in preparing your Carnot maps in the design process. Another alternative is to use an assignment called one-hot, that is, representing all states with the same number of zeros and a single one. This approach uses as much number of flip-flops as the number of states, but it may reduce the combinational part of the circuit considerably. If, for example, we decide to assign a binary number sequence to the states, we can replace all variables representing the states by their assigned values and obtain the state table in this form. An important step in the design of sequential circuits is the preparation of excitation tables. Excitation tables are closely related to the characteristic tables of the flip-flops. The characteristic tables can be seen as the answer to the question what the next state of the flip-flop will be for a given set of inputs. The excitation tables present an answer to the inverse question, that is, what should be the inputs to the flip-flop to reach a given state from the present state. Remember the characteristic table of the SR flip-flop. We express the next state column in terms of the present state Q of t wherever possible to have the table in a compact form. If both inputs are 0, the flip-flop keeps its present state, If one of the inputs are 1 and the other 0, the flip-flop will set or reset its state according to the inputs. Further, if both inputs are set to 1, the next state will be indeterminate. Using this information provided by the characteristic table, we can determine the inputs required for any transition of SR flip-flop. If the state is 0 and should be kept at 0 when the next clock pulse arrives, the set input must be 0. As we can read from the first two lines of the characteristic table, the R input can be 0 or 1, because for R equals 0, the flip-flop will keep its present state, which is 0, and for R equals 1, it will reset its state to 0 regardless of the present state. Therefore, the R input can be taken as a don't care condition for this transition. Other lines of the excitation table can be found by substituting the relevant value of Q of t in the characteristic table and finding the input values for the lines where the desired next state appears. Similar analysis on the characteristic table of the JK flip-flop can be done to derive its excitation table. Remember that the characteristic table of JK flip-flop differs from that of the SR flip-flop in the absence of indeterminate states. If both inputs of JK flip-flop is 1, the next state is not indeterminate, but it is the complement of the present state. This brings extra don't care conditions in the excitation table of the JK flip-flop. It turns out that whenever the present state is 0, K input is don't care, and the next state depends on the J input only. And if the present state is 1, the J input can be taken as a don't care condition. The excitation table of D flip-flop is the simplest one. The next state of a D flip-flop is equal to its input. Therefore, the excitation table gives the required D input for any state transition as the value of the next state. Finally, the T flip-flop is a toggle flip-flop. That is, the next state is the complement of the present one whenever the input T is 1. Otherwise, it is the same as the present state. This results in an excitation table where T is required to be 1 if the next and present states are different. For transitions to the same state, T should be 0. Now we can write how the design procedure should flow using the tools we described up to now. Of course, as in the combinational case, the starting point is the problem statement. That is, a description of the objective that the sequential circuit is required to accomplish. Using this problem statement, we can write down a state diagram or a state transition table. We know how to obtain one of these from the other. The next step has to be a check whether a reduction can be done in the number of states and applying any possible reduction. If the binary values of the states are not implied directly by the problem statement, one has to also assign them in such a way so as to simplify the design. Once the states are assigned, the number and the types of the flip-flops to be used in the circuit can be determined. There is not a fixed set of rules by which you can determine the type of the flip-flops. All we can say is a few rules of thumb. We can say that the SR and JK flip-flops are general purpose flip-flops. T flip-flops may be more useful, that is, may result in a simpler combinational part for implementing counters, especially whenever the count sequence follows a gray code. D flip-flops are especially useful where the task to be done by the circuit involves some shift operations among the output bits. Also, whenever the design will be based on state equations. Also, there is no reason why different types of flip-flops cannot be combined in the same circuit. The next step is preparing the excitation and output tables for the circuit. This can be done by using the excitation tables of the flip-flops we have just introduced. After this point, the design will continue as for the combinational circuits. That is, we can simplify the flip-flop inputs and the circuit outputs in terms of the inputs by using the techniques we have used in the design of combinational circuits, for example, Carnot maps. After obtaining the flip-flop inputs in a simplified form, we can draw the logic circuit diagram. Here is an example. We would like to implement a synchronous sequential circuit that does the transitions as described in this state diagram. There are no explicit outputs in this circuit, or you can say that the outputs of the circuit are the flip-flop states themselves. Therefore, we do not have any outputs indicated on transition arrows. The labels of the arrows refer to the input of the circuit only. We also see that the states are specified as binary values, which saves us any state assignment considerations. We can tabulate the transitions defined in the state diagram in a state table. Here we call the state variables as A and B, and the input as X. From this state transition table, it is seen that there are no two lines that matches for all possible next states and the output. That means no state reductions are possible. Let us obtain the circuit for the state diagram using JK flip-flops. Since there are 4 states, we will use 2 flip-flops. All this brings us to the preparation of the excitation tables. To do this, let us rewrite the state table so that the present states and the input X appear on the input side of a truth table. Also, keeping the excitation table for the JK flip-flop at hand will prove to be useful. The first line of this table shows a transition from 0 to 0 for both flip-flops. According to the excitation table of the JK flip-flop, the inputs J and K for this transition are 0 and don't care, respectively. The next line indicates a transition from 0 to 0 for the A flip-flop and a 0 to 1 transition for B flip-flop. Therefore, the inputs for A will be 0 and don't care, as it is in the previous line. The inputs JB and KB are read from the excitation table as 1 and don't care. In short, we can copy the required inputs for each transition from the excitation table of the JK flip-flop and fill out the excitation table of the circuit completely. As I said in describing the design procedure, the rest will be combinational design. We can now simplify flip-flop inputs as functions of the present states and the input. This is the Carnot map for JA. Note that we arrange the table so that X literal differs between 2 rows and different combinations of A and B literals form the columns. JA can be reduced to Bx prime. The Carnot map of Ka results in Ka equals Bx. Also, it turns out that JB equals X and KB can be simplified as A XNOR X. Thanks to the abundance of don't care conditions, we ended up with quite simple expressions. We can now draw the circuit diagram. We have 2 flip-flops in the circuit. The J input of the flip-flop A is driven by the signal Bx prime. K input is Bx. We draw the inputs of B as X and A XNOR X. Finally, we connect the clock signal to both flip-flops to obtain a synchronous circuit. To finish this example, we note 3 important points. The first one is that you may need extra circuitry to assure a specified initial state after the power is on. It is not the case here, but if you have any unused states, you can regard them as don't care conditions to further simplify your design. But in such cases, you have to make sure that these unused states do not lead to a lookup. We will have an example of such a case in a couple of minutes. As the next example, we will design a 3-bit binary counter. A counter is a sequential circuit with no inputs. Such circuits go through a prescribed sequence of states by switching to the next state at every clock pulse. Therefore, the state diagram of a counter shows the transitions only, without any input or output labels on them. The 3-bit counter here is required to count from 0 to 7 repeatedly. Let us design this counter using T flip-flops. Since there are no inputs, we don't need separate columns for the present and next states. We can write only the present states in the order they are counted. So the next state is simply in the next line. Since the counter goes back to 0, 0, 0 after reaching 1, 1, 1, the next state for the last row is in the first row. To tabulate the flip-flop inputs, let us remember the excitation table of T flip-flop. The T input has to be 0 if the present and next states are equal. It has to be 1 if they are different. The state of the flip-flop A2 changes from 0 to 1 when the counter passes from 3 to 4 and also from 1 to 0 as the count returns from 7 back to 0. Otherwise, the next state is equal to the present state. Therefore, the column for T2 will be as this. A1 flip-flop changes its states at every next clock pulse. This results in alternating values for T1. A0 is toggled at every count, so T0 is 1 always. We can easily simplify these flip-flop inputs. T2 is a function of two minterms of A2, A1, and A0, and is obtained as A1, A0. T1 hardly needs a Carnot map, since we can directly see from the truth table that it is equal to A0. And finally, T0 is 1. Let's draw the circuit diagram. 3 T flip-flops with outputs A2, A1, and A0. T0 is 1, T1 is A0, and T2 is A1 and A0. We complete the drawing with the clock signal. Now we will design a counter that counts 6 3-bit numbers, namely 0, 1, 2, 4, 5, 6, and then back to 0 again. In other words, we will skip 3 and 7. For this counter, we will use JK flip-flops. Here is the count sequence, which consists of 6 numbers, and here is the excitation table of JK flip-flop. We can use this table to find the inputs of 3 flip-flops, which will implement the digits of the counter. For transitions from a 0 present state, J input will be equal to the next state and K will be taken as a don't care condition. If the present state of the transition is 1, then J will be don't care, whereas K has to be the complement of the next state. Further, we can take the states that are not in the count sequence as don't care conditions. Filling out the excitation table, we can simplify the flip-flop inputs. In the Carnot map of J2, we see that it can be taken as A1, thanks to the don't care conditions. The same is valid also for K2. On the other hand, J1 can be simplified from its Carnot map as being equal to A0. For K1, we don't need a Carnot map because considering all don't care conditions in this column as 1, we can equate K1 to 1. For A0 flip-flop, J0 input is simplified as A1 prime, and again the column K0 reveals that it can be taken as equal to 1. Let's draw the circuit diagram. Here are 3 flip-flops of our counter. We connect both J and K inputs of the flip-flop A2 to A1. J1 is A0, whereas J0 is A1 prime. The K input of these 2 flip-flops are both connected to logic 1. Finally, we complete the circuit with the clock connections. A relevant question at this point is what happens if the initial state is one of the unused states, that is 3 or 7. To check this, we assume that the state of the counter is 0, 1, 1 and find the flip-flop inputs to determine the next state. To do this, we recall the characteristic table of the JK flip-flop. The inputs of the A2 flip-flop are both 1 because they are determined by A1. Therefore, this flip-flop will change its state to the complement of the present state, that is, to 1. Also, both inputs to the A1 flip-flop are 1. Therefore, the next state of this flip-flop will be 0. Lastly, the J input of A0 flip-flop is A1 prime, that is 0, whereas the K input is 1. So its state will be cleared at the next clock pulse. That means the counter will count to 1, 0, 0 if the initial state is 0, 1, 1, and then it will continue counting the correct sequence. Similar analysis can be done also for an initial state of 1, 1, 1. By checking the flip-flop inputs, we can see that the counter will switch to 0, 0, 0 after this state. This assures us that if the counter starts at 0, 1, 1 or 1, 1, 1 accidentally, it will resume its correct count sequence after the next clock pulse. We also have an example on the design of sequential circuits using D flip-flops. We will design a logic circuit that detects a sequence of 3 or more consecutive ones in a string of bits arriving on the input line. First, let us draw a state diagram for this operation. We can distinguish among 4 states. S0 is the state of having a 0 as the most recent arrival. S1 is the state of having a 1 after the most recent 0. S2 will denote that a pair of 1s are received after the last 0. Finally, S3 corresponds to the case where 3 or more consecutive 1s are received. If the system is in a 0 state, that is, if the last bit has been a 0, a transition will be made to S1 as soon as a 1 is received. If the next bit is also 1, the circuit will be in S2. In these cases, the output is 0. Whenever the third consecutive 1 arrives, the system goes to the state S3, while it will switch its output to 1 in doing so. It will be staying in S3 as long as the arriving bits are 1. In all these states, a transition back to S0 is required whenever S0 is encountered, meaning that the circuit will start from the beginning to count the arriving ones. This is the complete state diagram. Note that we have 2 transitions coming out of each state, one of them for input 0, the other one for input 1. To do the state assignment with least possible effort, let us denote each state with the binary value of its subscript. With these values of the states, we can list the state transition table. Now, to draw the circuit diagram, we hardly need to write an excitation table because the input of a D flip-flop is required to be equal to its next state. We can directly simplify the next states of the flip-flops. In other words, we need to obtain simplified expressions for the state equations. writing the Carnot map from the state transition table, we can simplify A of t plus 1 as AX or BX. B of t plus 1, on the other hand, can be simplified as AX or B prime X. Further, the output Y of the circuit is obtained as Y equals AX. To draw the circuit diagram, we will connect the expressions for the next states directly to the D inputs of the flip-flops. So we need AX, BX, and we combine them with an OR gate to obtain the input for the A flip-flop. For the input of the B flip-flop, we generate B prime X and then OR it with AX. We complete the circuit with the clock connections. As the last example, we will draw the circuit diagram for a 4-bit maximum length sequence generator. Maximum length sequence generators are devices that can count through all possible numbers of their bit size except 0 before repeating the same sequence. That means an n-bit generator will generate all n-bit non-zero numbers in a sequence. Such devices are useful in generating pseudo-random numbers and can find applications in coding and cryptology. You can consult, for example, books on spread spectrum systems for further information on maximum length sequence, that is, MLS generators. A simple 4-bit MLS generator can be obtained by implementing a shift structure as this. To generate the next number in the sequence, each bit is shifted to the next less significant location, and the most significant bit is taken as the result of the XOR operation between A1 and A0. Equivalently, this operation can be described by these 4 state equations. Such shift operations are easily implemented by D flip-flops, since the next state of each bit is the present state of another bit. All we need to do is to connect the D input of each flip-flop to the output of the one generating the next more significant digit. The input for the most significant D flip-flop is obtained by an XOR operation. In this way, the circuit generates the next 4-bit number at every clock pulse. And that's the end of this video, as well as my series of digital design videos. As you always do after watching these videos, go over the exercises in your textbook to check your learning outcomes. That is, that you can describe a sequential circuit by any of the following analysis tools if one of them is given: circuit diagram, state transition table, state diagram, state and output equations, flip-flop inputs and circuit outputs. And that you can apply basic steps in designing sequential circuits starting from the problem statement and leading to the circuit diagram.